Hi, everybody. Welcome back to our lecture series on statistics. In today's lesson, we're going to talk about the statistic called chi-square. Now, a chi-square analysis is used when we are looking to determine whether the observed frequency is different than what we would expect by chance. Now, chi-square it's also important to know that chi-square is used for nominal data or categorical differences. So when we have categories, we want to see whether one particular group or category is significantly different from another in terms of what we would expect, right? So another thing I will say is that all of the lectures leading up to this one are considered parametric statistics. So you can expect a bell-shaped curve, whereas in this one with chi-square, you're going to hear me say that it is generally speaking positively skewed data. Okay, so when we talk about chi-square and goodness of fit, we can do a chi-square with one variable of interest, or we could do a two-variable problem as well, right? So we would start off with some given hypothesis, and we would need to factor in, well, what would be the expected distribution or probability if everything were by chance. So chi-square distributions can be used for a lot of different things. For example, we know that in general, women in STEM fields are underrepresented. So if I were a physics professor, or I was doing research on the discipline of physics, better yet, I might want to know if there are, is there a disproportionate number of males relative to females in the physics discipline? So I would count all of our professors, males, females, and compare that against what we would expect by chance. Now, obviously, when we talk about gender, it's not binary, but I've made it binary to make things a little bit more simplistic for this example. Now, the shape of the chi-square depends on our degrees of freedom. Chi-square distributions are typically skewed distributions, that is to say positively skewed. However, if we had an infinite number of degrees of freedom, then we would get an distribution that matches the normal distribution. So how do we get the degrees of freedom, or how do we get the critical value? I'm going to go into the book that we've been dealing with for the whole semester. There is a table called the chi-square table, and I'm going to take you through this now, but what I want to do is actually stop sharing my screen so you can see it a little bit easier. So I'm going to go to the table. You'll see it's called Table G in this particular book. And at the top, you're going to see the critical value of chi-square. Now, with a one variable problem, we say that the degrees of freedom are the total number of categories minus one. So if I had three categories, we would say 3 minus 1. If I had 4 categories, I would say 4 minus 1. So whatever the number of categories are, that helps me calculate the respective degrees of freedom to get the critical value. So typically, if nothing is said, we assume that we're using an alpha of 0.05 or a level of significance of 0.05. And in addition, we assume two-tailed test, but that's not relevant to this table. But so those are your general assumptions. So we go across first and then down. We go across to find our level of significance. If it's 0.05, we look for that, and then we go down to the number of degrees of freedom, and that would help us find our critical value. So I'm going to go back into the slides and continue. So, all right. So here is the formula for chi-square. I'm going to write it on the board as well, but I'll come back to it. Chi-square is equal to the sum of FO minus FE squared over FE. So we're going to come back to this formula in a moment, but I want to define it. So on this particular slide, I use OE, but O stands for observed frequency, E stands for expected frequency. Not much different than in notes. So here would be an example. Suppose you were in a school-based speech and language pathologist and you wanted to determine whether or not the frequency of respondents differed based on one's level of experience or, dare I say, level of career. So early career speech and language pathologist, mid-career speech and language pathologist, or later career speech and language pathologist. So here would be the frequencies, and I'm going to write this on the board and we're going to come back to it. So for the first group, we have 10 years, right? 11 to 20, 21 plus. All right, so the first frequency is 57. That's how many respondents said that they were early career, right? There were 32 respondents who said they were mid-career. And then there were 11 respondents who said they were late career. So now let me work through the steps with you. So I'm going to stop my share for the time being. And we're going to add this up and we're going to get 100 respondents. So the sum of the FO column is 100. Now, how do we get the FE column or the expected frequency? Well, we can put 100 divided by 3, which gives us 33.333, right? I like to go 3 decimal places in general. You're going to see on the slides coming up, I didn't go 3 decimal places, but we're going to put 33.333 here. Okay, so now I add up the FE column. In general, the sum of the FO column and the sum of the FE column should be the same. Now, in this particular case, because it's a repeating number, we're going to have a rounding error. It's not going to be exact. So if I add up FE, I'm going to get 99.999. Okay. So the next step is to get a difference score. In general, the difference score should be 0, right? But again, we're going to have that difference. It's not going to be exactly 0 because of the rounding errors. So what I'm going to do is I'm going to take my calculator and we're going to calculate this. So I'm going to do 57 minus 33.333. And that's going to give me a number of 23.667, right? Then I'm going to do the same thing because we're subtracting FO minus FE. The next one I'm going to do 32 minus 33.333. And then I'm going to get a negative 1.33. And then I'm going to do the same thing with my final one, 11 minus 33.333 gives me minus 22.333. Now, if I add this column up, 23.667 minus 1.333 minus 1.333, I'm going to get something that looks like this, 0.001, right? Now, that shouldn't shock you because this is the difference between what's over here. So 99.999 plus 0.001 would give us the 100. But if the numbers were even, if they were not rounding, this number would match this, and this should be a perfect 0, as we talked about when we discussed difference scores in general. So the next thing I'm going to do is I'm going to square these values. So you see FO minus FE, I'm squaring it. And I said earlier that we square a value to remove the negative number. So I'm going to do 23.667, and I'm going to square that value. And I'm going to get something, and again, I'm going to have to round it. I'm going to use 3 decimals, but I'm going to round it. I'm going to get something that looks like 560.126. I lied, 127, right? Because we round that. Then we do the next one, negative 1.33, 3 squared, and then we get 1.777. And then the last one we're going to do is 22.333 in the negative, and then we're going to square that value. Okay, and then we get 498.763. Now, no problem. So really, we have everything we need, and we're almost up to the final part of this formula. So chi-square is equal to the sum of the frequency observed, or the observed frequency, minus the expected frequency squared over the expected frequency. So notice we have one more column. So I'm going to need to take these numbers here and divide by its respective expected frequency. So the first number was 560.127, and I'm going to divide that by its expected frequency of 33.333, and I'm going to get something that looks like this, 16.804. Now, the next one we're going to do is we're going to do 1.777 divided by 33.333. And then for this one, I'm going to get 0.053. And then the last one is 498.763. And I'm going to divide that by its expected frequency of 33.333 again. And I'm going to get something that looks like this, 14.963. I'm going to add these up. And then this, when I add up the last column, that is actually our chi-square value. Okay, so 16.804 plus 0.053 plus 14.963 gives us 31.82. So this is our chi-square value. This last number is our chi-square value. So we have to, because we're in inferential statistics, work through the 8 steps. So what was step 1? Step 1 was state the alpha. So our level of significance is 0.05. That's standard science. Step 2 was to state our null and alternative hypothesis. So what we're going to do is we're going to say the probability of getting category 1 is equal to the probability of getting category 2, which is equal to getting the probability of category 3. So notice how in the expected frequency, they were all identical of 33.333. The alternative hypothesis for the research hypothesis states that they're not equal, or at least one of them is not equal to the other. So that's that. Then step 3. Step 3 would be the number of tails. Again, this one doesn't have a distinction between one tail, two tail. So we're going to say two tail, which is the assumption in all of our tests. And step 4 would be our degrees of freedom. Now, I said the degrees of freedom are the number of categories minus 1. So what are our degrees of freedom? How many categories do we have over here? We have early career, mid-career, late career. So we have 3 categories, right? So we do 3 minus 1 gives me 2 degrees of freedom. Now, step 5 is to get our critical value. And I memorized this one, but if you go to the back of the book, if you do a 0.05 with 2 degrees of freedom, you're going to get a critical value of 5.99. Now, step 6 was what was our calculated test value. So we got a chi-square of 31.82. Now, is our chi-square value equal to or greater than our critical value? The answer is yes, 31 is greater than 5, right? So in this particular case, we are going to make our decision. And what is our decision? Well, we reject the null whenever the calculated value is equal to or greater than a critical value. So we're going to reject the null. Perfect. Now we have to do an interpretation. And for the interpretation, I'm going to say it in words, and I'm going to ask you to just note it. So typically, we would have 2 sentences that we would interpret it. The first one is, what was the test? What did you find? So using a chi-square analysis, we found significant differences in level of career or phase of career relative to what we would expect by chance. Now, you can then take a look and you see the vast majority of our respondents on the board were people who were less than 10 years in the profession. So they were early career. So our second sentence would be more specifically, there was an overrepresentation of early career speech and language pathologists relative to what we would have expected by chance. So now that's our first one. And I'm going to show you another way to write it as we move forward. But this was our hypothetical data, and I did it all by hand. Now I'm going to report it as we would go. So obviously the null hypothesis says there's no difference in the frequency of occurrence. And if there is, it's due to chance or except by chance, right? The research hypothesis or alternative hypothesis is, wait a minute, there is a difference in the probability of getting a given outcome. Now, I keep using the word alpha or level of significance. You might say level of risk, right? Because we're saying that we're willing to allow up to 5% error. Now, why is it that we are using a chi-square for this data? Is because we are dealing with mutually exclusive categories, right? And there's nothing objectively better about a person who's early career, mid-career, or late career. It's just a phase of career. It's a category. And it's an exclusive category. Either you're early, mid, or late career. You can't be in more than one category at a time. So here is the data. Again, I did it on the board using 3 decimal places. On the slide, I used 2 decimal places, but you will notice that the chi-square value of 31.82 came out the same whether we did 2 decimal places or 3. I like to use 3 because sometimes there's a small difference due to rounding error, so I use 3 places typically. So what were our degrees of freedom? As I said, it's the number of rows or categories minus 1. So we had 3 groups or 3 rows, and we subtract 1 and we get 2 degrees of freedom, which gives us the critical value of 5.99 that I put on the board. So when we compare our chi-square value with 2 degrees of freedom, we see that our chi-square exceeds the critical value of 5.99, and therefore it can be concluded that the distribution of speech and language pathologists by years of experience is not what we would have expected by chance. This is, as I said, there is an overrepresentation of early career professionals. So here is another one, and I'm going to have to erase the board and set this up. So let me erase the board and work my way through this one as well. I'm going to pause this, and then we will reconvene when I cleared the board. All right, so I erased the board, and we're going to look at, this time, we're trying to evaluate snack food preference. So we're trying to decide if there's an overrepresentation of people who like chocolate chip cookies, potato chips, or cheese doodles. So the data we have is there were 38 people who like chocolate chip cookies as their preferred snack. There were 28 people who liked potato chips, and then there were 24 who liked cheese doodles. So I'm going to stop my share for the time being and put that on the board. So we have 38, 28, and I already forgot what the snack food was. And cheese doodles was 24. So chocolate chip cookies, potato chips, and cheese doodles. So now, I don't know if you can see, but here we are. I set up the board, right? And I'm going to lift it up a little more, right? So we have our chocolate chip cookie people, our potato chip people, and our cheese doodle people. Now, same steps apply as the last one. We're going to add up our FO column to see how many participants we had. And if we add that up, we're going to get 90. So now, how do we get the frequency expected? So we say the total number of participants divided by the number of categories. So there were 3 snack foods here. So 90 divided by 3 is 30. Okay, so I'm going to put 30 in each of these. So 30, 30, 30. And if you play back the previous part of the lesson, I said that the sum of the FO column should match the sum of the FE column. In this particular case, we have a perfect match. And that's good for us, right? The previous example didn't work because we had rounding errors. So if you have rounding errors, you're going to have issues with that. Fine. So now we do the different scores. 38 minus 30 is 8. 28 minus 30 is minus 2. 24 minus 30 is minus 6. Now I said the sum of the difference column should equal 0. Again, that's what we have, right? So now we square these numbers to get our FO minus FE squared. So 8 squared is 64, 2 squared is 4, and 6 squared is 36. So what we have if we add this column up is 104. So now I'm going to do my difference, FO minus FE squared divided by FE. So for this first one, for chocolate chip cookies, the CC, I'm going to take 64 and divide that by 30, which was its expected frequency. And I'm going to get something that looks like 2.133. The next one I'm going to do is 4 divided by 30. And I'm going to get something that looks like 0.133. And then I'm going to do my last one, which is 36 divided by 30. And I'm going to get 1.200. Now I'm going to add this up, right? So if I add this up, I get 1.2 plus 0.133 plus 2.133. If I add that up, I get a total chi-square value of 3.466. Now, same rules apply. Once I have my chi-square, I'm going to run it through my 8 steps. So step 1 was our alpha. We said 0.05. Step 2 was our null hypothesis. We had 3 groups. So the null says the group observed frequency is equal to what we would expect by chance. The alternative hypothesis says the group's distribution is not equal, right? The probability of getting it is not equal. So, and again, 2 tails, that's the default, right? Then we have our degrees of freedom. Again, how many snack foods did we have? We had 3. So we do 3 categories minus 1 gives us 2 degrees of freedom. And now we're ready to go with our critical value. If we go to the back of the book, this is going to be 5.99 again. And our chi-square value was equal to 3.466. Now, you may recall we reject the null hypothesis when our observed score is equal to or greater than our critical value. So is 3.466 equal to or greater than our critical value of 5.99? The answer is no. So what's our decision? Our decision is now to accept the null. We have to accept the null because, again, our observed value is not equal to or greater. Now, in this case, then we interpret, right? This time it's going to sound like this. Using a chi-square analysis, we found no statistically significant differences in snack food preference relative to what we would expect by chance. So that's cool, right? So I've done 2 examples. The first example, we found significant differences. The second example, we did not find statistically significant differences. So I've shown you how to do both of them. All right, so let me go back into the PowerPoint and go full screen. So we did this and we found out that the snack food preference was not significantly different than we would expect by chance. All right, so if you had 2 categories, the truth is you could use a binomial distribution and calculate its value. And that would happen when you, I guess you square the normal distribution. It gives you the chi-square distribution with 1 degree of freedom. So that's that. Now, if you're going to use a chi-square, there are some rules or assumptions that must be met. As I said, each observation, each person who responds can only fall into 1 category at a time, and those categories have to be mutually exclusive. So you can't be early career or mid-career at the same time. We also have to calculate based on observed and expected frequencies. It has to be based on computations. And we expect a certain number of observations in each cell. And it depends on the number of degrees of freedom. If you had 1 degree of freedom or 2 groups, we expect you to have a minimum of 5 scores in each cell. With 2 degrees of freedom, we expect it to be 2 or more. And then if you have 3 or more degrees of freedom, it varies, so there's no set rule. So right now, I have taught you about the concept of a chi-square using one variable or one variable problem. But in reality, many issues we face are such that, you know, we don't explain an outcome using one thing. So we expect there to be a relationship between variables. So for example, if I were to do some form of a chi-square analysis between ethnicity and political party, well, ethnicity is a categorical variable, political party is a categorical variable, and we might want to know if there's some kind of relationship between the two. So the null hypothesis says, nope, the 2 variables are independent. The research hypothesis or alternative hypothesis says, wait a minute, they are related. So here is an example. Again, this would be if a researcher was doing a 2x3 design, confidence of high, medium, low, and athletic ability of high and low. This one I have to do slightly different to get my FE. Remember in the original one we did, FE is the number of participants, number of observations divided by number of categories. The rule for a 2 variable problem is we take, I'm going to use black again, right? So we take the row sum, multiply it by the column sum, and then we divide that by the total number of observations. Now, for this to make sense, I'm going to advance the slide and I'm going to work through it. And then I'm going to put this on the board and do it one by one. Now, our degrees of freedom, the calculation's different with a 2 variable problem. We say the total number of categories in our row minus 1, and we multiply that against the total number in our columns minus 1, and that'll give you your degrees of freedom. And then we calculate the chi-square. So this is where I want to set this up on the board and work it through. So let me erase the previous, and then we'll work through it. So let me stop my share, and I'm gonna pause for the time being and set up. Okay, so what I've done here is take what was on the PowerPoint and transfer it here. So this would be confidence, this would be abilities, right? So the numbers that are first represented are the observed frequencies. That which is in parenthesis are the expected frequencies that we have to get. So the first thing we need to do is get our totals. So 17 plus 13 gives us 30. 32 plus 43 gives us 75. Now, 11 plus 34 gives us 45. Okay, so if we were to add these 3 numbers up, we get 150 total observations. All right, the next thing we have to do is add across. So 17 plus 32 plus 11. So that should give us 60, right? Let's just double check. 32, 49, yeah, 60. And then this will, if we add up 13 plus 43 plus 34, we get 90. So notice whether we add these 3 numbers, we get 150. If we add down these 2 numbers, we get 150. Now, here's the deal. I said we multiply the row total by the column total. So if we were looking at 17, what we would do is we would go down to 30, go across to 60. We multiply those two numbers. So what's 60 times 30? 1800, 1800 divided by 150. So let's do that, because that's the division is the total number of observations. We get an expected frequency of 12. Great. Now, if we do 30 times 90 divided by 150, you're going to get 18. Now, if we add those up, 12 plus 18 gives us 30. So again, the observed frequency matches the expected frequency. And we do the same thing. So 75 times 60 divided by 150 gives us 30 here, right? And then we do 75 times 90 divided by 150 to get this one. That's going to give us 45. If we add up 30 and 45, we get 75. The next one we do, to get this one, we go to 11. The total is, let me just write totals so you know you're going down and across. All right, so the column total is 45. The row total is 60. So we're going to do 60 times 45 and divide that by 150, and we're going to get 18. Now, let's just double check, right? Because if we add across, this also has to match. So 12 plus 30 is 42 plus 18 gives us 60. So in our expected frequency, it matches the same way it matched down. So we're going to do the last one, 90 times 45, right? Divided by 150, that's going to give us 27. Now we want to add down to see if that matches 27 plus 18. Yes, it does. That gives us an expected frequency of 45. And now we can add across to see if this gets us 90. 18 plus 45 plus 27 indeed gives us 90. And then 90 plus 60 gives us 150. So no matter which way we slice it, the formula of multiplying the column total by the row total and dividing, it works. It works consistently. So the next thing we're going to do is we're going to do that same chi-square process that we did, but I'm going to transfer these numbers to the other side of the board. So let me set that up and I'll be with you again. There's a lot of moving parts. Forgive me for having to pause everything. Okay, so here we are again. I've taken everything that we had on the previous board where we took athletic ability and confidence, and I've abbreviated them as high, 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 medium, high, low, low, high, low, medium, low, low. Now, if I add up the FO column, I'm going to get 150. If I add up the FE column, I'm going to get 150. Now, the next thing that we haven't done are our difference scores. If I'm worried about making a mistake, the sum of the differences or sum of deviation should always be 0. So let's see what we get. So 17 minus 12 is 5. 32 minus 30 is 2. 11 minus 18 is -7. 13 minus 18 is -5. 43 minus 45 is -2. And 34 minus 27 is 7. Now, if you do this 7 minus 7, the first three cancel each other out. -5, -2 is -7 plus 7. Sure enough, if we add that whole thing, we get 0. So now we have to square this value. So 5 squared is 25. 2 squared is 4. 7 squared is 49. Again, 25. Again, 4. And again, 49. So let's add that up. Again, because I always like to add up all my columns. 25 plus 4 plus 49 plus 25 plus 4 plus 49. It's interesting the way we did it. The order actually, it replicated itself, right? 25, 4, 49, 25, 4, 49. So we add that up, we get 156. Now, the next thing we have to do is get the actual chi-square value. So we have to take this number divided by this. So what is 25 divided by 12? That's going to give us 2.083. And then we say, what is 4 divided by 30? That's going to be 0.133. What's 49 divided by 18? That's going to give us 2.722. 25 divided by 18. That's going to give us 1.389. And then, oh, we have 2 more. So 4 divided by 45. We get 0.089. And then we do 49 divided by 27. 49 divided by 27 gives us 1.815. All right, so now I have to add up all these numbers to get my chi-square value. So 2.803, pardon me, 2.083 plus 0.133 plus 2.722 plus 1.389 plus 0.089 plus 1.815. If I add that up, I get a chi-square value of 8.231 is our chi-square. So now, what is our alpha? So we're going to work through the 8 steps again. Our alpha is 0.05. Now, our known alternative hypothesis are a little bit different. Remember, with 2 variables, we say confidence and ability are independent. Now, when we say they're independent, we're saying they're unrelated. Whereas the alternative hypothesis would say confidence and ability are related. We have our 2 tails. Now, remember the degrees of freedom is R minus 1 times C minus 1. That's going to give us our degrees of freedom. So we had high, low ability. So that's going to be 2 minus 1 times 3 minus 1, which it's nice that we're keeping the same critical value is 1 times 2, or 2 degrees of freedom, which means our critical value is, again, 5.99. Okay, so what is our chi-square value? We got 8.231. So our decision is going to be, if the chi-square is equal to or greater, we're going to reject the null, which means using a chi-square analysis, we found that one's confidence and athletic ability were related. So that would be this example. Now, we're moving forward at a fairly decent clip. Let's go back into our slides. I do apologize. I have one more formula I want to show you. I actually may not be able to get to it. So let's see. All right, so we said that we could calculate the expected frequency, which would be in parentheses, by multiplying the total for the column by the total for the row and dividing it by the total number of participants. Now, there is another scenario, right? So with a 2x2 design, you could do the long-winded formula, or actually you could do shorthand. So what I'm going to do is I'm going to do that example. So let's create a 2x2. All right, so let's say we do in our 4 boxes, right? 20, 30, 10, 40. Well, we could add down, that's 30. Actually, I want to take the screen off for a second so you could see the board better. 30, 70. If we add that up, what's our total number of observations? 30 plus 70 is 100. And we could do the same thing here, 50, 50. So if we add 50 plus 50, we still get that process. Now, I said if you want to get the expected frequency, you could still do the same process. 30 times 50 is 1500 divided by 100 gives us an expected frequency of 15, right? 30 times 50, again, that's 15 because it's the same number on the other side. 70 times 50 is 3500 divided by 100 is 35, right? So we could do it the old-fashioned way, and we'll get our numbers. 15 plus 35 does give us 50. Again, 50, right? 35 plus 35 does give us 70. 15 plus 15 does give us 30. Great. So we could do it the old-fashioned way, or we could use this new formula that I mentioned. So with a 2x2, you can actually run the following formula. It is x squared equals n times AD minus BC squared over A plus B times C plus D times A plus C, and then B plus D. So what would that look like? Our N is 150 times AD. So A times D, this is A, this is D, is going to be 800 minus BC, 30 times 10 is 300. We're going to square that over AB is 50, CD is 50, AC is 30, and 70. All right, so let's work through this problem, right? So let me just make sure I'm able to put it all in view. Okay, so good. So actually, I was a little off. So here was our 2x2, right? I created this and I just started plugging in numbers. So this would become 150 times 500 squared over, now we have to get this number. And don't be afraid if you get large numbers, that's pretty normal. So let's see what we get. So 50 times 50 times 30 times 70 gives us a denominator of 5250. Okay, so now we're going to do this. So 500 squared times 150 is going to give us, just, 37. And let me just double check that. 500 times 500 times 150 gives us 37,500. and we divide that by 5 million. And this chi-square, we're going to do as follows. And we're going to get 7.143. Now, I urge you to do it the old-fashioned way, and you're going to see you get the same number. Now, I don't have the time to prove that, but do it the old-fashioned way. I use this 2x2 formula, and that's what I got. Pardon me. I made a mistake. It actually was, yeah. So that's our formula. Run it through, you're going to get the same numbers. All right, so this actually I made a mistake. Should have been based on multiplying it. Oh, that's what it was. Sorry, guys. It's 100 participants. The other example was 150. Should have been 25 million over that. And then let me redo the math. I should get 4.762. All right. So let's finish up the lecture. We're going to go back to sharing our screen. The rest of this stuff we can talk about conceptually. All right, so here we are. I've shown you all of the formulas. The rest of it you just need to know conceptually. So we talked about the 2x2. If we wanted to know the strength of association, there are two different ways to do that. We can do a phi coefficient or a Kramer's phi. We just did a 2x2, right? So in a 2x2, that's called a phi coefficient. That would give you the strength of association. Now, your phi coefficient is reported very similar to a correlation, which ranges between 0 to 1. And naturally, the closer you get to 1 is that results in a stronger effect or relationship. Now, if you have more than a 2x2, so if we did the example of the athletic ability and confidence, that one we use a Kramer's phi. So if any of your variables has more than 2 levels, you use Kramer's phi. And the same rule applies, 0 to 1. So that's our lesson. And I hope you've enjoyed this series. And I'm going to stop there.